Going back to the system that we have, so what we have is we have a processor and we decided to utilize the memory mapped IO, and as it turns out that processor in here actually can communicate with any of the subsystem here or here just by issuing certain addresses and getting these addresses. But what we're going to be doing is we're going to say, okay, this particular subsystem and this particular subsystem, we're going to just put them in the same address space as the whole memory space. And the processor, when it communicates with it, it will communicate through a bridge. From the processor perspective, it doesn't know what's happening in here. We as designers and application developers would know, but the processor knows that it's writing to some sort of a location in its own memory space. And what it knows, it's just communicating with some sort of a bridge in here. And the bridge will actually interpret these addresses. It takes it, well, if you're dealing with the MMIO subsystem, it'll take us through here, and then the controller in here will tell us like what's happening in there internally. The same goes with the video subsystem, which we're going to be talking about later. Okay, so a few specifications in here that are very peculiar to our space here, or our system. And the subsystems, both of them need 24-byte or in 24-bit byte addressable space, or as we know, we can take the least two significant bits and get rid of them and say they're 22-bit word addressable. Okay, so why do we need this? You might say, well, 2 to the 24 is really large. It's a really, really large number. That means I can actually have many rows or many bytes here for that memory, and it's really large. Do I really need all of that? And as it turns out, we won't need it for the MMIO, but the reason why we have that 24 mainly is because of this particular video RAM and the frame buffer in here. Well, as it turns out, for video, we need a lot of memory, and that's what we need it. We'll be focusing on the MMIO first, and then later in the course we'll actually go to the video subsystem and know it. But for now, what we're going to know is the following. Yes, the processor can handle 32-bit address, but we don't really need all of them. What we need is we need only 24 of them. So if you think about it, 2 to the 24 divided by 2 to the 32, if you calculate this, you're going to get 0.39%. So yes, we're utilizing 24-bit for the address, and we're using about less than 1% of the available memory space that processor can handle, which is okay. So even though that 2 to the 24 is really large, I'm still not utilizing the memory space for that particular processor. It can handle a lot more. It's even less than 0.5%, or like, yeah, 0.5% in here. Okay, so that's good. So then the next thing that I want you to know, so we have 24-bit for the address, for the internal addresses in here, the one we're going to be dealing with later. You can think about them as 22 word addressable, basically. If each one of these, if we arrange the four, instead of arranging them in 4 different rows, we arrange them in one line. Okay. Then now, next what I want you to know is one of these bits is going to be so that the processor or the F-bridge in here can know whether we're dealing with the subsystem, this one in here, or the video subsystem. And what we're going to do is we're going to take the most significant bit, which is bit number 23, and we're going to say if we set it to 0, that means I want to communicate with the MMIO. If I set it to 1, that means I want to communicate with that. So technically, I really only need 23 bits internally, 23 bits internally for the address, byte address that is, for this system and this system. Okay, so let's focus on the MMIO subsystem because this is what we're going to be spending the next few weeks on. So for the memory IO subsystem, we need to just, I basically ignored everything now. I'm just focusing on it. Based on the specification that we decided that it should accommodate up to 64 slots. So because it provides 64 slots, in order for me to figure out which one of these IOs I'm communicating with, I need 6 bits because 64 equals 2 to the power 6. So 6 bits are going to go to the slot number. And what we're going to do is I basically have in here these 1, 2, 3, 4, 5, and 6, basically 24 bits, the one that we decided that we need. Okay, so you can see that the most significant bit is now set to 0 because I'm dealing with MMIO. That basically just tells me whether I'm communicating with the video subsystem or the MMIO. But you're going to see that I only need 6 bits for the slots, and I'm just going to place them right here. I can place them anywhere, but just let's put a convention in here. So what we're going to be doing for the sake of expandability and simplicity, what we're going to say is each one of these in here, I'm going to give it 32-bit register or 32-bit words. Okay, so each one of them can actually have, if you think about it, I'm going to have 1, 2, 3, 4, 5, 6, 32-bit rows. Each one of them is a word that is 32-bit. So of course, if you multiply 32 or divide it by 4, it's like you'll figure out like how many rows of bytes you need. But for now, for simplicity, we're just going to say, okay, we have 1, 2, 3, 4, 32. This has 32. This one has 32. This one has 32. And each one of them has 32. So technically, we need 2 to the power 5 because that's how much is 32. So in order for you to know the offset within a within a memory, basically within an I/O, what you need to know is you need to know these 5 bits in here. So we're going to put them in here, and that's basically the register offset. So you might be wondering, okay, why do I need 32-bit for the GPO? The general purpose output is just basically probably connected to LEDs. I only have 16. I don't even need a whole 32-bit word. And you're going to see that it's, yes, you don't have to use all of the 32 available in each one of them. You might just use 1 or half or even 1 bit for that matter. And the reason why we use the 32 is just simplicity, because when we're going to have to build that controller in here, and if each one of them is separate, it's just going to create a whole headache. So what we're going to do is, okay, that controller is going to assume each one, if you're connecting something to it, it just should have that 32-bit register. It's just easier. Okay, so technically, if you look at it, 2 to the power 6 times 2 to the power 5, we'll add 6 to the 5. Really, what we need is we need 11 bits for the address. And that's basically, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 bits for the address. And that's if we're dealing word addressable. But if we're dealing with byte addressable, we need to put these 2 bits here, the least significant bits. And this is how we're going to actually access each one of these GPIOs.